Hi everybody, welcome to lesson 6.3, and we're going to start off with video 6.3.1. So we're going to continue on with those ideas that we were looking at last time. So idea number 3, a reaction will proceed to minimize its free energy. So it wants to minimize the amount of energy in the reaction, right? It wants to be at the lowest possible energy state. In other words, the position of equilibrium of a reversible reaction is explained by the free energy of the reaction. So we're going to look at a few scenarios here. So we'll look at the first scenario in the first column. When the change in the Gibbs free energy of reaction is less than 0, that is negative. That means the free energy of the system is decreasing. And the reaction in that case is going to be spontaneous. If it's going to be spontaneous, that means it's going to proceed in the forward direction. And Q is going to be less than KEQ, which also describes the reaction in equilibrium going in the forward direction. Now, if we switch gears and look at the opposite situation, where delta G reaction is greater than 0 or positive, that means that the free energy of the system is increasing, right? And remember, we want to move to minimize the free energy. So now the reaction is non-spontaneous. It doesn't want to do that. It doesn't want to have more energy. It doesn't want to go to a higher energy state. And it will proceed, but in the reverse direction. And Q will be greater than KEQ, again describing the direction of movement. Now, if delta G reaction is 0, the free energy is not changing, and the reaction is at equilibrium. It's not going to proceed at all. Well, I mean, you'll still have movement, but no net movement. And Q will be equal to KEQ. Now, the relationship between delta G and Q is given by this reaction, or this relationship here. Delta G reaction equals the delta G reaction at the standard state plus RT ln Q, natural logarithm of Q. Now, where R is equal to our gas constant and T is the temperatures in Kelvin. Now, we're going to use all of this information to fill out this reaction table in example 1. So we have 8 different trials here with the different initial pressures of both reactants and products. And then we're going to figure out our Q of each one, QP versus KP, delta G reaction, and the duration of the spontaneous reaction. I'm going to do the first one with you, and then after that I would like you to pause the video and see if you can figure out the rest. So remember, Q is products over reactants. Our reaction is here. Our products are going to be NO2. Our reactants N2O4. So QP, P for pressure, equals the pressure of NO2 squared, we square it because of the coefficient, divided by, so that's a product, divided by a reactant, pressure of N2O4. And we're going to use that for each of these calculations. Now, when I plug this into my calculator and I take 0.024 squared and divide it by 0.988, I end up getting about 0. So we're going to round to the 0.01 place, the hundredths place. So I will write 0.00 here. Now, if I compare this to our K is right here, 0.09. Is it greater than, less than, or equal to? Well, clearly 0 is less than 0.09. So Q is less than K in this case. The delta G reaction, plugging this in, up here, is negative 12.5. How did I get that? And I round to the 0.1 place, the 10th place. How did I get that? Well, I used this reaction and I plugged in everything that I needed up here, right? So you're given your delta G reaction at standard state right here. Your ideal gas constant is right here. Your temperature, 298 Kelvin. And our natural logarithm of Q, well, we just calculate Q right here. Now, in which direction does the spontaneous reaction go? Well, we just look at Q. If Q is less than K, I can refer to my handy chart we made and figure out that it goes in the forward direction. So this is in the forward direction. Okay, so right now I'd like you to pause the video and please complete trials 2 through 8 and then come back to check your work. Okay, welcome back. If you just want to check your work, you can go and fast forward this part. I am just going to work through each of these. If you have a question, you can pause wherever you need help. Doing my calculation, I got 0.02. Q is still less than K. plug this in, negative 3.2, and I'm in my forward direction here. Now I get 0.09 for my Q here. Now this one's interesting, because now Q is equal to K. That means we're at equilibrium, so the delta G reaction is 0. We've minimized that free energy available in the system, and we're at equilibrium. My next Q, negative, or not, sorry, not negative, 0.20. Q is greater than K. I now am swapping into positive numbers here, so 2.1, and I will go in the reverse direction. 0.38. Q is still greater than K. I get 3.6 and reverse. 0.64 is my Q calculated. Q is still greater than K. 4.9 and reverse. 1.00 for my Q. Q is still greater than K. 6.0 and reverse. 1.50 is my Q. Q is much greater than K at this point. Delta G reaction 7.0. Now, let's take a look at trial B, or part B. Using the values of QP and delta G reaction, in trial 5, how can we tell the direction of the spontaneous reaction? Or the direction of the spontaneous, that should say reaction, not direction. So if we look at trial 5, right here, and we go all the way across, we're going to look at Q. If Q is greater than K, that means it's going to be reverse, right? We're going in the reverse direction. Also, we can look over here at delta G. Our delta G is 3.6. That's greater than 0. So we know it's going to be in the reverse direction. Oops, not equal to, greater than. Good. Okay, in which trial is the system at equilibrium? How can we tell? Well, for this one, look at Q being equal to K and delta G being 0, right? We've minimized the free energy, and we're not going to go in the forward or the reverse direction here. So that's going to be reaction 3 or trial 3. In which trial is the reaction mixture at standard state? How can we tell whether the reaction will proceed in the forward or reverse direction at standard state? So for this one, we have to look at the delta G in standard state, which is 6 kilojoules per mole. And then we look at the delta G we calculated. Oh, 6. So that's going to be trial 7. Delta G equals delta G naught, which indicates standard state. And it's going to go in the reverse direction, because Q is greater than K and delta G is greater than 0. All right, let's look at part C. The plot of the free energy of the reaction mixture is plotted against the reaction quotient Q. So how is delta G reaction represented on this graph? So if we look right here, so this is the delta G at standard state, the change in it, of the products. And this is delta G naught of the reactants. And here's our reaction quotient Q. Now, the very bottom of the energy well, right here, is when we're hitting equilibrium. And that is when we are, of course, not having any forward or reverse reactions happening. No net forward or reverse reactions happening. They're, of course, still moving, but they're the same. And our free energy has been the lowest in the system. So this is the point where equilibrium hits. Now, where is our delta G of reaction? Where is the change? Well, if we look at the difference between products and reactants, that's going to be our change. So if I look at this level of free energy, so remember free energy is right here, this difference right here is delta G reaction. That's the change in the free energy of the reaction, the difference between the products and the reactants. Okay, let's go ahead and look at the next part. So idea number 4. Idea number 4 states that the, put it where you can see it, the sign of delta G reaction tells us the magnitude of KEQ. Since delta G naught reaction is reported at Q equals 1, so remember at standard state, its sign shows in which direction the reaction will go to reach equilibrium, and it tells the magnitude of KEQ. So if delta G reaction is less than 0, the reaction will proceed in the forward direction to reach equilibrium. So KEQ is going to be greater than 1. And again, that's going to go in the forward direction. And there's nothing new about that. We know when KEQ is 1, greater than 1, we're going to go forward. If delta G reaction is greater than 0, so positive, we're going to go in the reverse direction and to reach equilibrium, so KEQ will be less than 1 to get there. Now we can look at the relationship between delta G naught reaction and KEQ, and we can derive that using Q is equal to KEQ at equilibrium, and delta G reaction is equal to 0 at equilibrium. So we're going to plug those in here, and from that derivation, we are going to we are going to find this equation. Now this equation is given to you on your formula sheet, so no need to memorize it. But you can rearrange this equation by putting the natural log on the other side, the ln of KEQ, and then getting rid of your natural log by using base E. And you'll end up getting this formula. Now if you're not 100% sure how to derive this, or you don't think you'll remember on the test, it's worth memorizing this formula right here. I'll write a little note. It's worth memorizing this if you don't remember how to derive it. Of course, if you can derive it, no problem at all. And you're not stressed about doing that in a high pressure test situation, then no need to memorize. You can just use the one given to you and derive that. Okay, so this is the end of video 6.3.1, and I will see you in the next video for 6.3.2. Bye.